Welcome to the review session. So let's start off with the first question. What are the different types of fossils? Hey guys, here's Danny the dinosaur. Danny lived 65 million years ago. So we know that Danny, of course, has died. Oh, poor Danny. When Danny died, he became an original remain. Now obviously this is not a dinosaur bone, but this is a shark's jaw. But this gives you the idea of an original remain. This was the animal itself. So either we find bones, we find actual full whole animals like a woolly mammoth that's been preserved in ice. We find bugs, maybe small frogs or small birds preserved in amber. Or we find evidence similar to this but maybe with more muscle on it in tar. But these are all the original parts of the animal. So that's one type of fossil. The next type of fossil, so if we come back to Danny here. So poor little Danny, he fell. When Danny was on this planet, Danny roamed around. And Danny left a lot of footprints. And yes, these are his nice little footprints. This is a second type of fossil. So this is a trace fossil. This isn't his footprint itself, but it is it's evidence of his existence. Okay, so it tells us things like how tall Danny is, how big his feet, which obviously he's got ridiculously large feet, how much of his walking stride was. That's a second type. A third type is something called a mold and a cast. And I know it seems very random that I have a cake pan, but it's the same idea. So what happened is some creature falls into a lake and dies. And we can pretend like that creature made this impression in this cake pan. And that thing decayed away. Well, what do? We add cake mix to the pan and make a cake. It's the same idea. This is the mold, and when we take the cake out, that's the cast. Okay? It's not the actual animal, it's just an impression of the animal. So that's the third type of fossil evidence. Alright? The fourth type of fossil evidence, which I don't have, so we're going to come over here to my nice little whiteboard. The fourth type is something called an index fossil. So we can imagine if we look at sedimentary rock, which you guys all know at this point, an index fossil, and I'm just going to make a heart fossil, why not? That's an index fossil. And what this means is if I'm over, this is in Africa, let's say, and I see lots of heart fossils in this particular layer of rock. And then I go over, let's say, to Asia. And in the same rock, I find more heart fossils. That's an index fossil. So it is a fossil that is found all over the planet, but it's only for a short period of time, and it's only in a specific place. So it creates an index in terms of time. So we can measure that time on that index fossil. Let's just make a number up and say it's 500 million years ago. If we date this, we can then date all the rocks that we find that particular fossil in. So that's another type. That's the index fossil. I'm going to erase it. I'm going to stay here. And I'm going to talk about a carbon film. Okay, so a carbon film, we have to imagine I'm going to make a nice pretty little flower. Okay, and that pretty little flower lived. Well, if it got squished between a rock, this pretty little flower would then be on my rock. And so when a scientist finds this, I'm going to get rid of its stem for now, so we just have a little rock, a little flower. When the scientist finds this, it sees this carbon imprint. So this isn't actually the plant, it's its carbon that has left this impression. I guess you can't even say an impression, but has left almost like an artist's paintbrush on the rock itself. So remember, this is a rock, and this would be the carbon film that was left as a result of being possibly just squished between the rock for millions of years. Okay, so that's the fifth type. And the very last type, I want to make sure I get every one of them. The very last type is called petrified wood, and I don't have petrified wood. But what you can imagine is a tree stump. It dies, falls into a swamp. Over time, all of the water comes rushing through with different sediments. And those sediments kick out the cells, because you know that plants have cells, kicks them out and replaces them so that it makes it hard as a rock. So when we pick up that petrified wood, it literally feels like rock. And that's the sixth type of fossil. Question number 2. What processes create sedimentary rock? So what we've got here is we've got brown sugar. And what we're going to do is we're going to go over those processes that create sedimentary rock. So the first process is weathering. So weathering can either be done mechanically, whip, 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 so physical forces, or blowing it, which that's not really successful. But it also can be moved by water. So let's see what happens if we pour some water on this. Ooh, look at all that weathering. Okay. So what happened was we've weathered it, and now it's starting to erode. The erosion is going to be moving the sediments down, and then what we start to see, oh, look right there, you can see deposition that's going to start occurring because it's going to move and my mountain is starting to really goo up. Okay, so that's weathering, it moved, deposition, and erosion, it's moving away. So it started to break down, it's moving aside, it's being deposited, as we can see in the pan, all over the pan. Okay, so those are 3 of the 5 types. Give you 1 second to take a look at that and kind of process it. Now it looks like a big old brown goo ball. But that is the same idea. Now obviously this takes a really long time. Mine obviously did it very quickly. But weathering, blowing on it, taking the water and pouring on it. Erosion, it's moving away, depositing somewhere else. Oh no, there goes my mountain, it's starting to fall. We also have 2 other pieces to this. And it's done. Dun dun dun. I'm going to use this time for these. I'm going to go to some marshmallows. Okay. So once we have these events occurring, we have another event called compaction. Okay. So all it means is that I'm squishing this close together. After I've squished it together, we have sediments that fill in. So give me 1 second. A lot more small. And they squish together. So then I end up with a big old goo ball of marshmallow, but this is the cementation. So now they have cemented together. And when you see it out into nature, it looks like a whole bunch of random rocks glued together. And that's exactly what cementation is. So compaction is they've been moved really close together, and then we fill all those spaces with water and sediment, and it glues itself together. All right, the third question is, what is the difference between absolute age and relative age? Okay, so let's go over absolute versus relative age. And this is my daughter, Emma Grace. Okay, so when we think of relative age, obviously I am younger than she is. Just kidding. You know that she is younger than I am. So that is relative age. It's in relation to me. Absolute age is our exact age. So Emma Grace, how old are you?
4.
You're 4? Okay, now I'm not going to reveal my age, but obviously you know I'm older than she is, and that would be, we're going to say I'm 20. So that's my absolute age, where her absolute age is 4. You know she's younger than I am, that's her relative, but you know her absolute, which is 4. All right, the next question, so when we think about that absolute age that just came up, we have to address what half-life is, because that relates to absolute age. Here is a lonely little cookie. Now, when we think about half-life, obviously you all are very tempted to want to eat this cookie, but this can represent half-life, okay? So we've got 100% of the cookie. Half-life means that I have half that amount going away at some specified amount of time. So I'm going to take it. No, don't cut me. Yes, I'm going to cut you. And I have just, oh, not very good, cut that in half. So this half, which is going to eventually be in my stomach soon, has been decayed. Okay? So half-life, we have the amount that's left, undecayed, the amount that's decayed, which I just took away. Some amount of time has passed. I'm going to take that cookie and cut it in half again. This is decayed away. This is undecayed. Again, take and cut this in half. This decays away. This is undecayed. So this is half-life. Amount of time it takes for something to divide in half. Or the ratio of decayed versus undecayed, which is undecayed, atoms left in rock. Okay, so let's go through and calculate half-life. Okay, so let's look at this problem. I have element A, and it has a half-life of 350 years, so that's a very important number. The starting amount of element A is 62 grams. You discover a fossil that only has 3.875 of element A. So my question to you is, how old is the fossil. Okay, so let's go ahead, and I've created this chart, and we did this in class. Let's go ahead and solve this problem. So like I told everybody in class, we always start with a time of 0 because we're talking right now, present day. In the problem, the initial amount was 62 grams. And what we found when we were digging in the dirt or whatever was that we had that fossil that was at 3.875 grams. So we need to know this answer right here, okay? So I'm going to go through, I'm going to fill this side in because over here, all we're doing is dividing by 2. So we're just going to continue to go all the way down and divide by 2. So 62 divided by 2, we get 31. 31 divided by 2, we get 15.5. 15.5 divided by 2 is 7.75. And then, of course, we divide it by 2 one more time to get here. So now let's go over to time. When we do time, we always add to each one of these, we add the half-life. Okay? And the half-life of this particular sample is 350 years. Okay? So we take 0 and we add 350, which gives us 350. We take 350 and we add 350 to it again. This gives us 700. We add 350 again, we get 1,050. We're going to add 350 one more time, and that gives us 1,400. So our answer to the problem of how much time has passed, how old that fossil is 1,400 years based on our chart. All right, so the next question gets into these rock layers. So it's, what are unconformities, faults, and intrusions? Okay, so let's start with an unconformity. And you guys are probably familiar with these drawings because you worked with them in class. I'm going to ignore this drawing for now. We'll deal with that in a few minutes. But let's look here. So an unconformity, what it is that over time, so obviously we have our rock layers forming here, C, then B. Some type of weathering and erosion event has occurred and washed away sediment. And that is going to be represented where this red line that I've kind of here, but this red squiggly line, which I know I'm making a hot mess of this, but this is the unconformity. So this is telling us that erosion has occurred, it went away, and then something formed on top of it. The next thing we're going to go to is a fault. So the fault is down here, okay? And I'm going to highlight that fault with this blue marker. There's my fault. What this means is that due to some event on the earth, let's say a transform boundary, so I've got plates moving in different directions, the earth is actually broken and shifted. And it's represented with a nice, it's a straight line, but it's usually going to be at an angle. So we can see where this rock layer C has been shifted up, and B has been shifted up, and A has been shifted up. A, B, and C were already present, and then the fault occurred. So if I were to age it, the fault would be the youngest in this diagram, because these rocks had to be formed before they could break. The very last word up here, so intrusion, and this is igneous rock. This is where igneous rock sort of decides to melt its way up into sedimentary rock. And that's what I'm highlighting with this blue marker. Now, when we see these diagrams, we always want to assume that that igneous intrusion is going as far as it does, and it decides to stop, okay? Any layer it passes through means that now this is younger than it. So it's younger than B, it's younger than C, it is also younger than D because it passes through here. We are going to, just based on this diagram, going to have to assume that E is now the youngest because E formed after this did. Because when we look at these diagrams, there's no other evidence to suggest otherwise. Okay guys, so this is the end of part 1 of our 2-part series. So please make sure that you do actually go on and find the second part so that we can cover the remaining pieces of the material that is on your test.